So, in the previous chapter, the second moment method, it shows that when we have some random variable x, then it is very close to expectation with high probability if the variance is small. So this is very useful. But in many cases, I mean, we want to show, in other words, second moment method shows that a certain event happened with high probability. But in many cases, we want to just show that the certain event with positive probability. It doesn't have to be high. So for example, if we are flipping n coins, each comes up with a head with probability half and tail with probability half, and they are independent, then it is likely that the number of times that we get the head is like half n. So with the second moment method, we can actually show that with high probability, it's very close to half n. The number of head is close to half n. However, we can actually also show that there exists positive probability. So with positive probability, all n are heads. All n trials give you head. The probability that it happens is half to the n, which is positive, which is small but positive. So, in this case, the expectation is not really what we want, but because all the trials are independent, there is this, positive probability that all of them happen because they are independent. As long as there are many independent events, each one of them happens with positive probability, then there is a, positive probability that all of them happens. Or equivalently, all of them not happen also. The number of heads become 0 is also, lower bounded by the probability is lower bounded by the half to the n, which is positive number. So here, what makes this, approach works is the independency. Independency over this event ensures that we can make sure that all of them happens or all of them not happen. So one question we can say is that what if we have almost independency? In other words, we have weak dependency over the events. Can you make sure that all of them happens or all of them not happen? So we first have to define what this weak dependency or loose dependency, what this means. So let A1, AN be events. And we say compound events. Compound event specifies the occurrence of AI, say for I certain set, and non-occurrence of AJ for J in T, where S, T are disjoint subsets of bracket n. And we say that an event B is mutually independent of A1 to AN if B is independent of each compound event specified by disjoint subsets S and T of bracket n. So as I mentioned before, so this defines mutual independence. So A1 and say P1. Give me a moment. So A3 and B A2. In that way, so probability of A1 happens when each of the A2 or B3, A2 or A3 happen is half. So A1 is independent of A2 and A1 is independent of A3. The probability that A1 happens when A2 and A3 all happens is 1. Probability of A1 happens when A2 but not A3 happen is 0. So A1 is independent of A2 and A1 is independent of A3, but A1 is not mutually independent of A2 and A3 because these compound events, assuming that the probability of A1 changes, so they are not independent. So mutually independent is stronger than pairwise independence. So this can provide way to measure the weak dependency. And we want to prove local lemma, as it's written in the name of the chapter. Erdős and Lovász, 1975, proved this following local lemma, which is called Lovász local lemma. So, at the time, Lovász was young and Erdős was an established mathematician. And Erdős, whenever Erdős presents this theorem, Erdős stressed out that it's Lovász's theorem. So it's called Lovász local lemma. So these are events such that each event is mutually independent of some set of all but and most the other events. So it's mutually independent of all events except the most the events. And suppose that each event holds with probability m most p for all I, and E times P times D. This E is the natural constant, the base of the natural log. Then the probability that all events does not happen is positive. You can actually avoid, there is way to avoid all the bad events, all the events. So this is the local lemma that we want to prove. And actually we want to prove a more general version. Let's say definition. So version which is more general than that. Let's say we have events in a probability space. We say that a directed graph D whose vertex set is bracket n, the index set from 1 to n, is called a dependency digraph. Okay, let's write it this way. It could be digraph or it could be graph. It doesn't really matter. You can consider the graph as same as the digraph with both directions there. Then, so a graph can be also considered as a digraph. This is a dependency digraph for the events A1 to AN if the following holds. For each I, the event AI is mutually independent of all the events AJ where IJ, where J is not the out neighbor of I. So we have A1, A2, A3, A4, A5. We add on H if A1 can be depend on A3. So we have this digraph, and this A1 is mutually independent of all the events which is not out neighbor of this. A2 is independent of all the events which is not out neighbor of this. A5 is independent of all the events which is not out neighbor of this. And with this, we can actually state the local lemma, which is a general version. So suppose that D is a dependency digraph for the events A1 to AN, and suppose that there are real numbers x1 to xn between 0 and 1 such that the probability of event AI is at most xi times you consider all the out neighbor of I. So you consider all the events which are depending on which can affect the event AI, and we subtract xi from 1 and then we multiply them. If this holds for all I, then the probability that the probability that we can actually avoid all the event. So these AI are the bad events that we want to avoid. It's strictly positive, which is at least 1 minus xi all multiplied together. So remember, these xi are strictly smaller than 1. So this is strictly positive. So we can actually show that, in particular, with positive probability, no events I holds. So this provides that we want to design some random procedure, and there we want to show that we can actually avoid all the bad events. Then what you have to do is you just come up with this number which satisfies this equation, this inequality. Then you automatically show that with positive probability we can avoid all the events, all the bad events. So next time we will actually prove this, and then we see some application of this.